What is the most useful idea?
Small examples.
Yes, here we should use a small example on what?
Maybe the number of like unique positions, or like the number of like positions that appear.
Yeah, here we have how many positions do we have here?
All 144.
No. As look, 144 is a result of something, okay? So it's not good to use a small example on a result of something, okay? 144 is because of what?
12 times 12.
Yeah, so we should use a small example on what?
The number of numbers in the clock.
Yes, we can consider this one is M and use a small example on M, okay?
Okay.
So for M, for example, the first time that we can check is what?
Probably 2 would be the most.
Let's check 1 first, okay? So these are the cases 0, 1, 1, 0, 1, 1.
What is 0?
Okay? And we
What
should
is 0
consider
be?
mod 2. Agreed?
Is
For
0
example,
12?
here we can say the numbers are 0, 1 to 11, and we should consider mod 12. Agreed?
So 0 is 12 then.
So 0 is here M2, yes, M2. So 0 mod 12. So we consider mod 2 and M is 2, right? For M1, it's obvious. For M1, 0, 0 to 0, 0, 1 way, right?
Mm-hmm.
For M2, how many ways are there?
Two.
Okay, 2, let's check. 0, 0 can go to 0, 1 and 1, 0, right?
Yeah.
Okay. This one can go to 1, 1 or 0, 0, right?
Mm-hmm.
1, 1 can go to this one or this one, right?
Mm-hmm.
This one also can go to this one. This one can go to this one, right?
Mm-hmm.
Okay. So, if we go from here, then we have to go like this, or counterclockwise, right?
Yeah.
So 2 ways. Now let's consider M3. For M3, we have 0, 0, 0, 1, 0, 2. 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, right?
Yeah.
Okay, here we should consider mod 3. For this case, calculate how many ways are there.
I don't know how to solve this with 3. It's not complicated.
Okay, so here we have we can add first part or in the second part, right?
Okay.
It means that we have 2 directions, right? We
Yeah.
can call each of them as a point. So it means that from each point you can go to the right or up, right?
Yeah, that's what I've been doing.
Okay, so here we consider 2 parts, something like this. Let me write it with this 1, 2, 3, 1, 2, 3, 1, 2, 3, right?
Mm-hmm.
Okay, and we should pay attention that from here also we can go to this point, right?
Yeah.
So the directions are this one, for example, this one, and this one, and so on, right? And for example, when you reach this, from here you can go here or here, right?
Mm-hmm.
Okay. Now we want to use casework, okay? So we agree in the beginning we can go to right or up, and we can multiply it by what?
2.
2. Yes. If you go like this, then what can we conclude? Can you tell me out degree of each vertex is equal to what?
1.
Out, yeah, in the cycle, what? Yes, but possible movements. If you consider possible movements, what's out degree of each vertex?
What do you mean possible movements?
Possibilities means you can go to right or up, right? If you consider all
So,
possible movements, the out degree is 2, right?
uh-huh.
And what's the in degree of each vertex?
1.
2, 2, like out
Why is
degree.
it 2? I thought you only traveled to every vertex you went.
No, I say consider this part. If you consider this, do you agree in degree and out degree of each vertex is 2?
Yeah.
This
Well,
one,
what about, okay.
for all I, di plus and di minus is 2, right?
Yeah.
Okay. Now here. But in the cycle, we know in degree and out degree of each vertex is 1, right?
Yeah.
Okay. So if we erase it, let's remove this one, this one, this. Okay, so we go like this and we multiply by 2, right?
Yeah.
Okay. Now, because of this direction, you can conclude that there are some directions that we have in our cycle. What are those directions?
Like, what do you mean directions of the cycle?
For example, you should say, okay, we should have this direction, something like this. Okay, you
You
can
can go,
conclude that we should have some directions.
yeah. Well, you can go to the end and then loop. You can't loop back around, so you just have to
Look, when
go
when you
up.
have out degree, it means that we don't have this edge anymore, right?
Yeah.
And because this one should have 1 degree, we have 2 in degrees in total, right? So when we remove one of them, we should have this edge. Understood?
hmm
Okay, what else?
Well, that the point needs to go back to the original point, so you can draw that like
Tell me
arrow.
which row, which column. Consider this one is first row, first column. Which row, which column to which row?
First row or first column, second row.
First
That
column,
point needs to
second
go
row,
back.
this one.
Yeah, it needs to go back to 0, 0,
It has to go
right?
back to 0, 0.
Yeah, to finish the
We don't
loop,
have
right?
this edge. This edge is not exist.
Why doesn't this edge exist?
Because look, from 0, 0, you can go to 0, 1. You cannot go counterclockwise.
Oh, right.
Okay.
Oh.
You can conclude one more edge exactly similar to this one. Try to figure out.
The only really, I guess from first column, third row has to go to the third column, third row. Like that.
This one?
Yeah.
Because we don't have this, so we don't have this out degree, so we should have this out degree, right?
Yeah, or it should like go that way. It doesn't have to. Not one arrow, like two different arrows.
Let me check it again. Look, we know that from here we have these 2 out degrees. But we can have this out degree, right? So
Well, like two different arrows. two separate arrows.
Tell me exactly one of them so I can. From which point to which point?
1 3 to 3 3.
1 3 1 3 is this one. You mean this?
1 3 to 2 3. Just draw both of the arrows.
2 3 this one.
Yeah.
To what?
And then to 3 3.
This, right?
Mm-hmm.
Because you can't have this, and you should use 1 out degree and see. So we can conclude these two. Can we conclude any other thing? For example, we have this in degree. So we can't have in degree to this. So we concluded this. So we determined these three, right?
Wait, what about the first one? What about the first arrow? The first arrow.
What about this one?
Yeah.
We don't know. We
Why
should
is,
use casework.
why is there no
It can go like this or like this. And in degree can be like this one or this one.
okay.
We've not removed any of them to determine, okay?
Okay.
Okay, now let's consider second movement. From here we can go right or up, right?
Mm-hmm.
Okay, so let's consider both of them. So you should consider this one or this one. Okay, now like for example for this one, when you add this edge, we can remove which edges? Or we can add which edge?
What do you mean add which edges? You need a
Like the previous action.
out degree now. Well, you need an out degree now, so you draw the only out degree. So either goes. So you have to go up because you go back to the original, and your loop ends. Right.
Mm,
Draw the
from
out degree from there.
here we cannot go like this, but we can go
Yeah, so go up, right?
up. Then
Yeah.
what?
Then from here, well, you already drew the edge from, so you go back to that. So you go to the new one, and then from there you can either go up or right again.
No. Look, do exactly the same thing that I did. From here we remove. We don't have this. So
What do you mean remove? What do you? I don't know what you're
look,
talking about.
from here, do you agree you can go like here? It has two in degrees, right? This one. Agreed?
Okay.
From here and here. But do you agree you cannot use this because you selected our degree of this one is to the right, not to the up. So we don't have this edge, right?
Yeah.
So when we don't have this edge, we should have this edge. Understood?
Okay.
So we should use this approach again and again. So we cannot go this. We have to go to this point. Okay.
Okay.
Then what are the other edges that we can determine?
I mean, from here you have to. That has to go up.
Yes, it has to go up. What else?
And then we already drew that degree, so now you're on point. You're on 0.33, which has to go. It already has an in degree, so now it just has to. It already has to go to the 0.13.
Yes. Then what?
And from one, we've already reached every point now, so now we have to go back.
Yes. Finish. One good case, right?
Yeah.
What about this one?
You need to go. You need to go to the right from that point. It has to go to the right.
On this, we have to go right. What about this? Maybe we go like this.
Oh, wait.
So try to determine
Wait.
some edges.
You can't. Yeah, you can't go left. Okay.
I didn't say you here, right or up? You said
Yeah.
you have to go right. I said, what about this case?
Yeah, right and up.
Right and up. But look, we prefer to determine the edges that we have to place them. Let's first focus on them. Okay, then we don't need to use a lot of casework and in the end remove some of them. Try to find the edges that we have to place them. Try.
From 3 3 has to go into 3 1.
Let me check. From 3 3 it has to go to 3 1. This one.
Yeah.
What about this case?
Well, but then your point 3 1 doesn't have an in degree, right? And how
3
you
1.
reach
It doesn't have
3
any
1.
degree. Yes. Because we went to this, so we don't have this one. It doesn't have any degree exact, so we have to go back. Determine more.
From 1 2 has to go to 1 3.
From
Or is it 1 2 should go into 1 3.
yes, because we don't have this, so we have to have this. Exactly. What else?
Well, it has to
I
have an
think
out
we should
degree.
consider two cases, right?
Yeah, which of those 2 points goes back to the original? Whether it's 3 1 or 1 3.
Okay, so let's check here. Look, because we have this one, we don't have this one. Let's write them with dotted points. We don't have this one. Because we have this, we don't have this one. Because we have this one, we don't have this, we have this one. So we don't have input to this. And because we have this one, we don't have to this one because we have this. We don't have this because the input is to this one. We have this because we go input. We don't have this because we go output like this. We don't have this one, right? These are
Yeah.
something. So if we consider here, example, we don't have this one, we have this one. We can from here. Okay, so if we check, we can say we can go from this point to this point or this point, right?
Mm-hmm.
Okay. Then what happens? It goes like this, like this, like this. And 1 point before determining. We agree from here, we cannot go here, or we can go to this point. But if we go to the right, okay, so let's draw them again. When we go to the right, we cannot go like this, agreed? Because then it is a closed cycle, right?
Mm-hmm.
So you have to go to this point, agreed?
Yeah.
And you have to go like this, and it's a good case. If you go up, then this one. From here, you cannot go to this one again, it will be a closed cycle. So we have to go to this point, this point, this point, this. Now it's a good case, right?
Mm-hmm.
So what's the answer equal to?
These are all unique. So 6?
Exactly, it's 2 times 3, 6, okay?
Yeah.
Okay, now that we found this, we should try to find a relationship. We should also check 4. 1, 2, 3, 4, and then copy. So in previous case, we had 6 cases. Now we want to check this. Try to check N4 first on your own.
Okay. I feel like this casework is too complicated. I'm just trying to write it out, but I feel like I keep having to make cases.
Uh, let me tell you something. Look, if here we understood that, for example, when we determine one edge, then we can determine some other edges, right?
Yeah, that's what I'm trying to do.
Yeah, so I tried for solving this problem. Here we have 4 edges, right? In general.
Yeah.
I
Yeah.
tried to determine how many edges do we want to select from this, then we can determine other edges. And at first I wanted to try this. So I said, suppose if we don't have select any of them, let me tell you the cases. If we don't select any of them, it will be like this. If we select only one of them, do you agree it's not important to select this one or this one or this one because it is a loop. All vertices are symmetric. Do you agree it's not important that we select this edge here or here?
It's not important?
It's not important because look, we want to create a cycle. When we want to create a cycle, this one is not important, this one is not important. All of them are similar. Agreed?
Okay. Yeah.
Because look, this is first column, second column, third column, fourth column. Each one go to the next. So when you have one edge, it's not important that you place it here or here, okay?
Okay.
So without loss of generality, I place here. Then for 2 edges. For 2 edges, we should consider these cases. They are adjacent or they are not adjacent, okay?
Where are you placing edges like that? What does that kind of mean?
I mean edges, this one,
Yeah.
this
Like
one,
those are you have to have those edges.
exactly. So we should only check this one, and then for this case, 3 of them. These 3 and then this, okay? And then I
Okay.
want to consider. I say, okay, here we don't have this, so we should have this one. Similarly, we should have this one, we should have this one, we should have this one, right?
Mm-hmm.
And for this one, we should have input. So for all of them, we should have this, 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 and this. Agreed?
Mm-hmm.
Okay. So here we shouldn't have input to this one. So we should go here, 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 right?
Mm-hmm.
Again, we cannot go here, so it would be here, and that's a contradiction, right?
Mm-hmm. Yeah.
Okay. For the next one, we go like this. It means what? It means that we cannot go here. So we have to select this one, right?
Yeah.
We don't have this one, means output should go this. We don't have this one should go here, and this one should go here, right?
Mm-hmm.
Okay. For this one, output is this for this one. We cannot have this, so we should go like this, right?
Mm-hmm.
This one cannot go here, so it goes like this. This one cannot go here, so it goes like this, right?
Why can it not go to like the right?
Because if it
Oh,
goes
it
to
just
the
has to
right,
be
then
the
it has 2
yeah.
inputs, right?
Yeah, yeah.
So it goes to the up.
Okay.
Then what can we
Well,
determine? This one
that
cannot go to the right, so it should go to up, right? Cannot go to
yeah,
right, it should go to up. Cannot go to right, so we should have this, right?
yeah.
Okay. This one cannot go here, so it should go to this. This one cannot go here, so it should go, right?
Yeah.
This one cannot go here, it should go like this. This one cannot go here, it should go like this one. This one cannot go here. Oh, so here we have problem, right? No, 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 no. We don't have
Mm,
problem. It can go like this, right?
yeah.
And they agree it is good and it is unique.
Yeah.
So it is 4 choose 1. 4, right?
Where was your oh, you're saying four based on the original.
All of them are similar, so one of them is select and the rest will be unique. Okay?
Why are they all similar?
Because look, this is first column, second column is after this, third column, fourth column, then first column is again after this. It is like a loop. 1 to 2, 1, 2, 3, 4. So if we select this one or this one or this one or this one, they are same. Agreed?
Yeah.
Okay. Because let me tell you, for example, GIB, it's not important to start from this clock or start from, for example, this one. This, because they should be all of them on a cycle, and you should see how many cycles are there. So it's not important to start from each of them. We don't have any starting points, right? Because they are on the cycle. Agreed?
Mm-hmm.
So let me 4 choose 1, 4 choose 2, 4 choose 3. So check this one. See, is the rest of the path unique, or we reach contradiction, or what? When you check, you will see that for each of them, you will reach contradiction, or the path will be good. One good way or 0 good ways. So check this one.
So for the first case, I end up getting like that I'm forced to create a loop that doesn't include all of them.
Okay, so reach contradiction, right?
I think so.
Okay, we
So I
cannot
recheck
go
the
right, we should go up, right? Here we went
yeah
up, so we should have this. Here we cannot go up, so we have this, right?
yeah
Here we don't go like this, so you have to go like this one. You cannot go to the right, so you have to go to up. Then for this one, you cannot go right, you have to go to up. You cannot go to right, you have to go up, right?
yeah.
We can determine
And from 1 4, you have to go back to 1 1.
1 4. You cannot go
1
like
1.
this, you have to go like this, right?
Yeah.
Um, then you can go like this one. This one, can we determine any other stuff?
2. What's it called?
You
4
have to go.
3
You
has
have
to
to
go
go
to
like this, right?
yeah, and also 4 3 has to go to 1 3, right?
This one.
So yeah, 4 that goes into 1 3.
Why? Why it cannot go like this?
Well, that the one on 1 3 needs an in degree.
On this one needs in degree. So in degree from here we don't have. So we should have this one, right?
Yeah.
So because this one doesn't have in degree, so we should have in degree like this, right?
Yeah, but then 3, the one on 4 3 needs an in
Uh,
degree also.
we
So
don't have also this one, so we have this one, right?
okay, but 4 3 also needs an in degree.
4 3 needs in degree,
Has to come
so
from the
we have
left.
to go like this, right?
Yeah.
Yes. So we go like this one,
And
this one,
now
this one, this one, this
one
one, this one.
one
It
one
is a
3 needs an
closed
out
loop.
degree now, so it has to go up.
Let's see here. Look, if we go like
Create a
this, you
loop.
go like this one, this one, this one.
You just see
Uh,
1 3 needs to have an out degree. It
exactly.
has to
You
go
should
up.
go like this, right?
Yeah, the loop.
And then
Made
it's
a
a
loop.
closed loop without having all vertices, right?
Hmm.
So have you checked this one or not?
It's not the same. Then.
Are they same? We should check it because look, they are not adjacent. Here they are adjacent, right?
Okay.
But if we check, we can go with we have this, so we don't have this, so we have this in degrees. So here we should have out degree. Here we don't have out degree, so we should have in degree from this. Here we don't have out degree, so we should have out degree to this one, right?
So,
Here we don't have like this, so we should go to this one. And for in degree, we don't have this, so we should have this part, right?
yeah.
For this one, you should have in degree. You don't have from this, so we should have like this one. In degree, you don't have this one, so you have to have this one. For in degree, you don't have this one. We have this one for out degree. This one, this one, this one. We have out degree. So we have this. Okay, now for this one, it cannot go to the right. It goes to the up, right?
Mhm.
This one cannot go to the right. This one cannot go like this, so it goes to this one, right?
Mhm.
And what else? Here we go, this one. And this one cannot go here, it goes here.
Yeah.
And it cannot go to the up, it goes to the right. Again, we have a closed cycle without all vertices, right?
Mm-hmm.
So 4 choose 2 is bad, 4 choose 1 is good, 4 choose 3. Now let's check this one. So look for this one. We know that we have this in degree, out degree, so we don't have this one, so we should have this. Now we have in degree to this, so we don't have this part. So we have this. And because of this edge, we don't have this, so we have this. We don't have this, so we have this, right?
Yeah.
For this one, we don't have this, so we have this. And we don't have this one, so we have this one, right?
Mm-hmm. And that one has to go back to the origin.
Mm, yeah, we don't have this, so
So we
we
have
have this, right?
yeah, but we
We
also
don't
have one for
in
the
degree
one.
this one, right?
Yeah.
Okay, so from here you cannot go to the right, you should go to the up. You cannot go up, you go to right. You cannot go up, you cannot go up, you go to right.
Yeah.
And then you should go. And it considers all of them, right? So 4 choose 3 is good, right?
Yeah.
Okay, so it is 4 choose 1 plus 4 choose 3, okay? Now, if you check some cases, it will be, and it is 8. For this one also, if you check like this, after that we can check this. You will see 3 choose 1 works, 3 choose 2 works, it is 6. Can you guess that it is sigma n choose k such that what's the relationship between k and n?
Uh, K is on.
If you check 5, let me tell you. If you check 5, you will see 5 choose 1 works, 5 choose 2 works, 5 choose 3 works, 5 choose 4 works. Then can you guess n choose what numbers work?
4 choose 1, 4 choose. Okay, so for
4
2,
choose,
it's 2 choose 1. For 3, it's 3 choose 1 plus 3 choose 3.
yeah, 3
And
choose
for
1,
4,
3 choose
it's
2.
4
So
choose 1,
you should
3
check
choose
n
3.
choose which numbers. As a hint, 6 choose 1 works, 6 choose 5 works. Then if you check 7 choose 1 works, 7 choose 2 works, 7 choose 3, 7 choose 4,
So
7 choose 5, 7 choose 6.
there's like pairs that add up to work, that add up to like 7, or add up to n.
Yes,
Like
when we
1,
have 1, we
6.
have 6, 2, 5, but which pairs?
All the ones that add up to
But
n.
here we don't have 6 choose 2 and 6 choose 4.
One of the numbers needs to be odd.
There should be a relationship between n and k. What's the relationship?
And k are relatively prime.
Exactly. GCD of k and n should be 1. Okay? So by checking cases, we have this. We should prove this. Okay?
Okay.
If you check for any of the cases like this, we can prove, but we should place, for example, considering this row, the next row, and all these things. I don't remember how I prove, but you can try it as homework. Okay? Prove
Mm-hmm.
this. Okay, and if when we have this for 12, the answer is equal to what?
1608.
Okay, let's check. It will be 12 choose 1, right?
Yeah.
2, 3, 4, 5, 6, 7, and 11, right?
Mm-hmm. Yeah.
So 12 choose 1 and 12 choose 11 are equal. 2 times 12, 24, plus 2 times 12 choose 5, right?
Yeah.
This part is what? Is 12, 2, 12, 11, 10, 9, 8. 1, 2, 3, 4, 5 over 5, 4, 3, 2, right?
Yeah.
5 to 10, 4 times 3, 12. So 9 times 8, 72. 2 times 72, 144. 144 plus
Mm-hmm.
144 is 4, 8, 5, 1. So
Yeah.
24 plus 1584, right?
Yeah.
It's 801608, right?
Mm-hmm.
Okay.